Well, hello everybody. We're going to cover section 5.3 inverse functions. And so we're going to talk about inverse. Some of this is going to be review and some of this will be new. First of all, we are going to take the derivative of the inverse and we'll talk about what that means in a little bit. But first we're just going to review some inverse stuff. So you're given this set of points and you want to find the inverse of all of those points. So if you could pause the video and try those, and then we will go over them. So now that you haven't had a chance to go over these, your inverse points should be 4, 1 would be the first one there. The second one would be 5, 2. I'm just switching the x and y places. Then 6 and 3, and the final one would be 7 and 4. So that is inverse to those guys. And then, so basically what we're saying here is that if we have the domain of G, then it is the range of Y. So basically we're switching the x and y places in all of these, and that's what the inverse function is all about. And so we use this notation with a little -1 to talk about the inverse. And so then if we do f of the inverse of x, we get x. And if we do the inverse of f of x, we also get x. And so that leads us to our definition here, that if g is the inverse function of f, then we get f of g of x will equal x, and also g of f of x will also equal x. And so then that's how we will know it's an inverse. And so if g is the inverse of f, then f is the inverse of g. All right. And then as this goes along, a function does not have to have an inverse function, but if it does, the inverse function is unique. And basically what this means is there's no plus c family. So it's not a whole bunch of them, it's just one function as we go along. And so then to find the inverse, take the opposite operation of the given function. For example, if the function has addition, you would subtract. And if the function had multiplication, then you would divide. Right, and those are the inverse operations, and that's what you're used to doing. So make sure you get all of this down, pause it if you need to. All right, so then in Word, so I would like you guys to pause this and fill this out before you watch this part. It says what happens in words to x. First x is cubed, then multiplied by 2, and then subtracting 1. The inverse is the opposite, and so in the order we would go, we would make this, we would add 1 first, then we would divide by 2, and finally we would take the cube root. And so that is what we're doing when we're doing the opposite. So our goal here is that if the inverse of f equals g, then basically we're just trying to figure out what that would be. If my original function was this, that would be the cube root of x plus 1 divided by 2. That would be the inverse of it. And so then we want to verify that this is the case, so you might want to pause here and verify that f of g of x and g of f of x is an inverse. So f of g of x means I'm putting this g of x into f, so f of g of x will get me 2 times the cube root of x plus 1 over 2 cubed minus 1. And so that's me putting in g of x into f of x, and if I simplify this guy down, f of g of x Well, like cubing a cube root gets rid of that, so I get 2 times x plus 1 over 2 minus 1. And if I multiply and divide by 2, I believe those guys go away. So I'm left with x plus 1 minus 1. I lost the parentheses because I did the multiplication. And then f of g of x will turn into, when we add and subtract the 1, we get just x. So then g of f of x is me putting f of x into g. So g of f of x would look like this, would be the cube root of, I see an x now, so I'm going to put in 2x cubed minus 1 and plus 1 divided by 2. And so that's how that one looks. So g of f of x would be, well, if I get rid of the parentheses, I can add and subtract 1 up there, so I'm left with 2x cubed over 2, and I'm taking the cube root of all of this. So then g of f of x would be dividing by 2 gives me the cube root of x cubed, and then hopefully we know that the cube root of x cubed is just x. So this verifies that these guys are inverses. And the way that we find inverses, the alternate method to find the inverse, is if we have y equals 2x cubed minus 1, instead of thinking of it like we did up here, basically what we did before is we switched the x and y's places, so we would get x equals 2y cubed minus 1, and at this point, by switching these guys places, we could then solve for the y, and it'll give us the inverse function. And that's what we would do. We would add the 1, so it would be x plus 1 equals 2y cubed, divide by 2, x plus 1 divided by 2 equals y cubed. And so then y, if we take the cube root of this thing, we get x plus 1 all over 2. So those are the different ways of going about finding inverses and proving that the inverses are actual inverses of one another. Right. So now a couple things that we need to kind of think about is the existence of an inverse function. And not everything has an inverse function. So a function has to be one-to-one in order to have an inverse. And so what that means is it needs to be strictly increasing or strictly decreasing. So it might look something like this. This would be always increasing. We might have a function that does that, that's always decreasing. These guys are considered one-to-one, meaning that for every x there is only one y. And so that is what we're kind of dealing with when we go through here. So if x is strictly monotonic, monotonic means always increasing or always decreasing. So both of these functions that I drew up here are monotonic, and then we would just talk about whether or not they were increasing or decreasing. Now, if you remember, we did a vertical line test to determine if things were functions, but if you know anything about inverse functions are a 90-degree turn from that, so we don't do a vertical line test to test and see if it has an inverse function. We do a horizontal line test. Do a horizontal line test because this will determine if the function is one-to-one when, because think about it, if you draw a horizontal line, if I'm drawing horizontal lines up here into this function, if I was to turn it 90 degrees, they become vertical lines, and then we determine whether this guy is actually a function or not. All right, so the graph below can help us kind of see what's happening here. You can see in this first one here that it looks like, if I'm drawing horizontal lines, so far so good, but this next one, we have a little bit of a problem. So this guy will not have an inverse, as we know. Over here, horizontal line test, I draw a horizontal line. Any place I draw a horizontal line, I get just, it only crosses once. So therefore, this guy has an inverse. And so we can, this one, since this one fails, it has no inverse here. And over here it has an inverse, and so we could find it if we needed to. And if we found it, if this guy was equal to y, we could work our way around this thing and figure out which one it is. And I think I got my graphs backwards. I think these guys are different, but I yeah, I think I got my graphs backwards. I think this guy is that one and that one is oh well. You guys can look at on the worksheet. They're correct. All right. So then we're going to talk about properties of inverse functions. And the properties of inverse functions are basically dealing with what happens here. So basically, if f is continuous in the domain, then f inverse is continuous on its domain. Right. If f is increasing, then f inverse is increasing. And if f is decreasing, then f inverse is decreasing. And if f is differentiable, then f inverse is also differentiable. And finally, if we're talking about a point AB, then the inverse would be BA, and we'd establish that at the beginning of this. And so we're looking at this function, and this is what we're dealing with as we go. So as we continue on with this, we're talking about the derivative of the inverse function. And this isn't terribly tricky, but what ends up happening here is that because these guys are inverses of each other, we're basically taking the derivative of the function with the y value substituted in, because g of x is the y value of the inverse, which basically means we need the x value of the original function. And it gets a little confusing on how this works, but we will kind of go through a couple examples as we do this. All right. So what happens here is that, all right, so we want to find the inverse of the derivative of the inverse at 9 in this function. All right. So if I was looking at this, if I took the derivative of the original function, I get 2. All right. And if I have the point here for f of x has the point something in 9, because in the inverse of x, this guy is 9 and then something else. All right. And so when I take the derivative of this function, because it is equal to 2 at all times, then the derivative of the inverse will be equal to 2 at all times. All right, and so let me kind of show you how this works. All right, so if I need to figure out what my x value is, then what I would do is, since 9 is the y value of the original function, because it's the inverse x value, that's what we're looking at here. So what I do is I just say 9 is equal to 2x plus 5, because it's the y value. And if I solve for x, I'm going to subtract 5, so 4 equals 2x, divide by 2, and so then my x value is 2. So that's the original x value there. That is the y value for the inverse function. And so now if I take the derivative of, if I want to take the derivative of the inverse at 9, it is the same as me taking the derivative of the original function at the x value, which is the y value of the inverse. All right, and in this case, it is always going to be, it's going to give me a fraction of 1/2, because the derivative of the original function at 2, so the derivative up here at 2 is 2, because it's a line that would look something like that. So it always has a constant slope, so the inverse slope would be 1/2. All right, and that's really what we're looking for. Now that one's a fairly easy one, because we can kind of work our way through this one. It gets a little more complicated when the functions aren't necessarily just linear. And so we want to find the slope of the inverse at x equals 3. So what this is telling me is that I want to know what the inverse, the derivative of the inverse, when the x value of the inverse is 3. So I kind of like to make this little table over here. I've got f of x, I've got f inverse of x, And just so I can think about it, so this is the x value here. I need to find the y value. I'm given the y value of f of x. So in order for me to find this, I'm going to put my y value in here and for f of x and say 3 is equal to 1/4 x cubed plus x minus 1. Well, if I solve this, set it equal to 0, I'm going to subtract the 3 across the equal sign. Or actually, yeah, I'm going to subtract the 3 across the, or actually I'll add the 1 across the equal sign and get 4 equals 1/4 x cubed plus 3 plus x. And since this is not a factorable function, what I can do is I'm going to have to graph this thing. So at this point, I will have to graph, and it didn't have to be that way. I could graph it like this: 1/4 x cubed plus x minus 4 equals 0. I could graph it that way either. This one I would put in like y1 equals 4, and then y2 would be the 1/4 x cubed plus x, and then to find out where they intersect. This one down here, if I put this in y1, if I put that into y1, I'm looking for where it crosses the x-axis. All right, and so that's really what I'm looking for. And when I do that, and I'm going to let you guys do that if you'd like, when I do that, I get the value of x is 2. All right, and so that's where it happens. And so now that that happens, basically what I'm going to do, if I want the derivative of the inverse at 3, it is the same as me taking the 1 over the derivative at 2. All right, so that's what we're flip-flopping here. And so if I do my derivative at 2, well, if I take the derivative of this guy up here, take the derivative of the original function, and say f prime of x is equal to 3/4 x squared plus 1, and put in f prime of 2, well, I get 3/4 times 2 squared plus 1. This guy ends up being 4, and 4 times 3 is 12. 12 divided by 3 is 12 divided by 4 is 3, so 3 plus 1, so I end up with a value of 4. So for my derivative of my inverse function, I end up with 1 over 4. And that is the slope of the inverse function. All right, so let's try it again. So we got this guy over here, and we want to find the inverse, the derivative of the inverse at 4. And again, pause this anytime just to make sure that you can work through this problem. This would be a good one since we just did the previous problem. Pause it and see what's going to happen here. All right, so what I know is that I have an f of x that has a y value at 4, and over here my inverse of x has an x value at 4. So again, I'm trying to figure out what's going on here. So most likely, I'm going to set my y value of f of x equal to f of x. And if I subtract this 4 across the equal sign, I get 0 equals x squared minus x. I can factor out an x and get this. So this happens either at 0 or at 1. Well, they should have the same values there. And so what we have, since we don't have the same y values, remember that this graph is originally a parabola that looks like this, which does not pass the horizontal line test. So the inverse function is going to probably look something like that. And so what we're going to find is at 4 here, at somewhere out here at when the x value of the inverse is 4, so 1, 2, 3, 4, we're going to have two different y values that work for us that are going to get us two different slopes. So we're going to have, in this case, we're going to have 0, 4, and 1, 4 would be a place. And just because the inverse is not a function doesn't mean we can't do this. So we're going to deal with that, and we're going to deal with that. So one should be looks like a positive slope, one should look like a negative slope. And so as we go about this, well, again, we are going to take the derivative of the original function, and so that gets me 2x minus 1. And so then the inverse derivative of x is 1 over 2x minus 1. But then if I'm going to do this at 0, then I get 1 over negative 1, which is a negative 1 slope. And if I do it at the value of 1, then I end up with 1 over 2 minus 1, which is a positive 1 slope, which I said would probably happen. There's your positive 1 slope. There's your negative 1 slope because this thing is a parabola. That's what we're trying to find. And again, this works for functions or not functions in this case, but for the inverse. The function is, the original function is a function, but the inverse is not a function. All right, without some domain restrictions. All right, so then we're in the last one here, and we're given this table. And with this table given, we're asked to find the inverse at 6. All right, so the derivative of the inverse at 6. So let's think about this. Let's kind of go about what we did before. If I'm going to take, if I have f of x and I have the inverse function of x, well, the inverse function at x, they're giving me is 6. And so over here, I'm going to make my y value 6. All right, so if that's the case, then I need to figure out in f of x, when my y value is 6, what is my x value? Well, I see that as a 2, so I'm going to put 2 in there for each one of those. And so then, if I want to find, so basically, to find the derivative of the inverse at 6, so to find the derivative of the inverse function, that's supposed to be a negative 1 there, at 6, it's the same as saying 1 over the derivative of the original function at, in this case, the x value of 2. So I got to go to my x value of 2 here, and I got to find the derivative of that at that value. And so the inverse derivative at 6 is going to be 1 over 4, because that is the derivative of 2 of f of x at 2. And so that's kind of the way these guys need to work it out as we go through this. So this is the section, so we need to make sure that we're working on our homework today, and we'll do some more practice on Friday.